on number 5 here. We want to calculate the time of 1 year on Mars by setting centripetal force and gravitational force equal to each other. And then they give us the mass of Mars, the mass of the Sun, the radius of Mars's orbit, okay, on that. So Mars is a satellite of the Earth. So I can still say this, FC equals FG. All right. Then I can say that mv squared over r equals big G times the mass of the Sun times the mass of Mars over the radius of Mars's orbit squared. And this, of course, will be the mass of Mars over here on this side because it's the thing moving in the circle. All right. So right off the bat, mass of Mars is going to cancel. So I'm just going to get rid of it from both sides of the equation. So I have less things to worry about. I'm looking for period, not for speed. So I do need to do a substitution here, or do this in 2 steps, find v and then solve for t. I don't like that. I like to just substitute. Okay, so v is going to equal 2 pi r over t. So I'm going to take the v squared out of there. I'm going to put in 4 pi squared r squared over t squared. Okay, so I've squared that formula and I plugged it in for v. Taken v out and plugged it in instead. Since I have r squared on the top and an r on the bottom, they will cancel. Okay, and I'll be left with just an r on the top. All right, now I want to solve for t. So now I've got to do the real nuts and bolts algebra of this problem. I'm going to move t squared over to this side by multiplying both sides by it. All right. Then I'm going to move the radius of Mars's orbit over to here. This is also the radius of Mars's orbit. So what do I get when I multiply r by r squared? R cubed. All right, so that's going to come over here, and we're going to have a cube on that r. And then I'm going to divide both sides by big G times the mass of the Sun. That'll leave me with t squared. I just want t, so I'm going to square root that. There are a lot of exponents in here. That's okay. Okay, we just have to make sure we put them in our calculator. All right, so 4 pi squared times the radius of Mars's orbit, which is 2.3 times 10 to the 11 meters, cubed, as it appears in the formula. All right, and then I'm going to divide all that by 6.67 times 10 to the minus 11 times the mass of the Sun, 1.99 times 10 to the 30. Okay. When I punch all that into my calculator that I forgot to start up, I should end up with 6.0 times 10 to the 7 seconds. Okay, but we'll figure it out here in just a second. Eventually. All right, so we're going to start out with 4 pi squared. All right, and we're going to multiply that by, in brackets, the 2.3 E11 cubed. Right, I'm just going to get that. So that's the top. I'm going to divide that by what's on the bottom. So 2 sets of brackets there, 6.67 E negative 11. Okay, 1.99 E30. All right, close the brackets on that. I need to square root that. All right, that's 6.0 times 10 to the 7. Okay, and that's in seconds. How do I get it into years?
You divide by 3,600.
Okay.
And that would give you how many hours, I think?
Yep.
And you divide it by 24, give you how many days, and then divide by 365 to give it
365.25. Got to account the Earth's orbital period is 365.249 whatever days. That's why we have a leap year every 4 years, because it actually takes an extra quarter day to get all the way around. So yes, absolutely the right idea there. Okay, whoop, not 365.25. Delete that. Okay, and that's going to give us, 1.9 years. It takes almost twice as long for Mars to get around the Sun than the Earth. So if you lived on Mars, you'd have half as many birthdays. Sad. Less cake. Okay. All right, and the other ones giving us trouble? It's usually the ones that involve that substitution that end up being a little bit more troublesome because you just have that little bit of extra algebra. Okay? All right, if there aren't any other questions on the satellite stuff, okay, then we're going to move on to gravitational field strength, which is pretty straightforward, pretty quick, right? And then we'll do some practice with that. All right, so if you can find that bit in your notes or just have some paper out. Okay, so up until this unit, we've really treated gravity like any other force, which is odd because it's not. Okay? Most of the forces that we have dealt with are what we would call contact forces. That means they actually have to be in physical contact with the object in order to exert a force. Normal force is a contact force. Friction is a contact force. Tension is a contact force. Okay? Gravity isn't. Do I have to be in contact with the Earth's surface to be attracted to it? Nope. Okay? If that was the case, nobody would ever fall. Okay? You could jump off buildings and you'd be okay, right? Because gravity couldn't touch you because you weren't touching the Earth. Gravity doesn't work that way. Gravity is what we call a field force. Field forces act over an area of influence. Okay? So other field forces would be magnetism and electricity. Okay? You'll learn, actually there's a whole unit in Physics 30 on electricity and magnetism called fields and forces. Okay? Gravity is also a field force. That is, it has an area over which it can influence the movement of objects, can exert a force. Right? So that means I don't have to be in physical contact with an object to feel the effects of its mass on me, okay, or the mutual effects of our masses on each other. Everyone all right with that idea? Okay. So is the moon caught in the Earth's gravitational field? It's attracted to the Earth, right? Then it's caught in the Earth's gravitational field. Technically, everything is in the Earth's gravitational field. But the further away from Earth you get, what would happen to the strength of that field? It's going to decrease exponentially, right? So we can say, yeah, sure, the Earth's gravitational field extends infinitely, but its effects practically do not. Okay? Now we can see the effects of that if we look at how big our solar system is, and we look at how far out there are things that are still orbiting the sun. Okay? The sun's gravitational field is immense because the sun's mass is immense. Okay? All right, so gravity is a field force because it exerts a force without being in physical contact with another object. Okay? And we can measure the strength of that field as acceleration due to gravity. Okay? Field strength is not a force. Field strength is the rate at which you are attracted to that object. Okay? So what's the strength of the Earth's gravitational field right here? 9.81 meters per second squared. Or, more technically, but also equally valid, newtons per kilogram. Okay, if you divide newtons by kilograms, you are left with meters per second squared after all. Okay, so field strength is typically measured in newtons per kilogram. So for every kilogram of mass you have at this location, you would experience 9.81 newtons worth of force. That's how field strength works. Okay? All right. So if we're looking at the Earth and the Moon, obviously they have a mutual gravitational attractive force on each other. Okay? Field strength simplifies that down to more what we see and experience every day. And that is that the smaller object is caught in the larger object's gravitational field. All right? And so as a result, that object moves towards or orbits the larger object. Everyone okay with that? Okay? So field strength is very much a measure of the bigger thing doing something to the smaller thing. So it was actually Michael Faraday who came up with the idea of the field. He was working with magnetic fields and electric fields, but he's the one who discovered that there are some forces that don't require you to be in contact with the thing in order to exert a force on it. His big kind of demonstration of that would have been taking a bar magnet and putting it on a piece of paper and then sprinkling iron filings all over it. Okay? When he did that, what he found is the same thing we know now is true about the Earth. Okay? If this is the north end of the bar magnet and this is the south end of the bar magnet, the iron filings will line up along what we call the field lines. Okay? And even gravity has field lines. Okay? But essentially, you get all of the filings working along these fields here, along these lines of influence. Okay? And that's what the Earth's magnetic field also looks like. Okay? So gravity works the same. Anything caught or near the Earth is going to be influenced by the Earth's gravitational field. Right? So it eliminates the need for imaginary, invisible, magical strings connecting everything. Okay? Because, I mean, we know that for the longest time having magic invisible strings was like how you explained things like this. It's not a contact force. It doesn't require a string, okay, to be attached to something else. All right, so if Earth was alone, if there was nothing around the Earth's gravitational field would, for all intents and purposes, look pretty symmetrical like that. Okay? Is it perfectly symmetrical like that? No, because the Earth's not. It's not perfectly round. Okay? Its mass isn't perfectly distributed either. Okay? Not only is it not perfectly round, it's a little squished end to end, there are parts of the Earth that are a little heavier. Okay? I mean, there's maybe more continents over on one side, so there's more mass over there. Okay? So its mass isn't perfectly distributed, but for all intents and purposes, the Earth's gravitational field would be pretty symmetrical. But Earth's not alone. What else is here? The moon. Does the moon have mass? Does the moon have its own gravitational field? Is the Earth caught in the moon's gravitational field? Do we have evidence of that? The tides, right? The tides are evidence that, yes, in fact, we are also under the influence of the moon's gravitational field, and that it does overlap the Earth. All right, so if we're looking at like field strength, okay, the formula looks like this. Have we seen this formula before? We absolutely have. We just always see it like this. Okay? It's really just manipulated. But is there another way other than this to calculate force of gravity? If I'm standing on the Earth's surface, should those two things be equal? Right? I should get the same number if either way I calculate that, right? I can definitely say those two things are equal. Okay? One of the masses in the equation on the left is the mass of what? If I'm talking about me standing here on the Earth's surface, is the mass of the Earth. One of these is the mass of the Earth. The other one is me. Which one's on both sides? Me. I'm on both sides. Okay? Because this would calculate my weight, not the Earth's weight, right? The Earth doesn't really have weight compared to itself, right? So, my mass cancels. Is that important? Because G is the same no matter what your mass is. G is only dependent on the big mass. That's the Earth. Okay? So, that formula is on your formula sheet. Okay? The gravitational field strength is big G times mass 1 over r squared equals little g. Right? It's really just a manipulation of Newton's universal law of gravitation, eliminating the smaller mass and allowing us to calculate what the gravitational acceleration or field strength would be. Are field strength and force of gravity the same thing? They are not. Field strength is acceleration due to gravity. Force of gravity is force. They are not the same thing. The most common mistake I see on a unit exam question about gravitational field strength is somebody doing this. Okay, that calculates the force of gravity, not the field strength or the acceleration due to gravity. It is really crucially important that you read the question carefully so you know whether that question wants the field strength or the force, okay? Because they are two different things, right? Now, typically on a unit exam, I will boldface, italicize, and underline the words field strength so that you don't get confused, okay? But I'll still get some people that will do it the wrong way, okay? Just make sure you understand that field strength measures acceleration, force measures force, okay? They're different. Okay, everyone all right with what we've done there? Okay, so really what we're doing is going force of gravity divided by mass, so that's newtons divided by kilograms, and that gives us meters per second squared, or newtons per kilogram, okay, for our units. Would I accept either unit? I have to. They're the same thing. Newtons per kilogram is meters per second squared, so either one of those is fine. All right, so we were saying Earth's gravitational area isn't as simple as Earth all by itself. The moon is also a part of this. Okay? So now we see that the Earth's gravitational field is somewhat skewed. Right? Here's Earth. Okay? Here is the moon. Is there a spot in between them where you would be equally attracted to both? There is. Okay? We call those Lagrange points. They're actually everywhere. Okay? There's points between the Earth and the Sun that would be a Lagrange point. Okay? Basically where there would be zero net gravitational attraction. So if you're sending a spacecraft to the moon, is this a point you need to know the location of? Yeah. You don't want to be accelerating towards the moon when you cross that point, because what will happen? Yeah, you could, not only are you going to have the force of your spacecraft pushing you away from Earth, but now you're going to have the force of the moon sucking you in as well, okay? You're going to crash into the moon, right? When they put things on the moon or in orbit around the moon, once they pass that point, they have to flip them over. So that now, when they activate the engines, they're actually pushing against the gravitational attraction of the moon so that they slow down. If they don't do that, they'll accelerate towards the moon just because of the moon's gravity. Okay? They need to stop that, so they turn the spacecraft around. Right? If you've ever seen the SpaceX thing try and land, right? Like it actually every time just fires, it elevates itself and points the engines at Earth and just lowers itself to the ground. Okay. All right. So this here point would be obviously the point where the net gravitational attraction would be zero. Is it closer to the moon or the Earth? Yeah, it's way closer to the moon. That's not even really to scale. Right? Why is it way closer to the moon? Yeah, the moon has way less mass. Okay? The moon's got less mass, so it's got less gravitational field strength around it. So it is much, much closer to the moon. All right? Okay, what if I'm over here? What's happened to the vector on some of these field lines? Do they point towards the center of the Earth? No. Okay. Also something you have to consider if you're trying to send a rocket to the moon. You don't point the rocket at the moon. Okay? Where do you point it? You point it where the moon will be. when you want to land on it. The moon's moving, okay? If you aim at the moon, you're gonna miss it because it's gonna move away, right? So if I'm trying to land a spacecraft on the moon and the moon is orbiting this way, I need to point my spacecraft this way so that I arrive at the point where the moon is going to be when it gets there, which means I have to cross some of these wonkier gravitational field lines, okay? All of that has to be taken into effect when they plot the course, when the astrometrics people, okay, are figuring out, okay, when do we have to tilt the spacecraft, when do we have to fire which engine to keep it on course. All of those field lines have to be accounted for. Okay? When you're trying to push something even up into orbit, sometimes you have to still consider it. Okay, it's basically saying the same thing. According to this formula, the one that's on your formula sheet, is there still that inverse exponential relationship with radius? Yeah. The gravitational field strength decreases exponentially with distance, same as force of gravity does. They're dependent on the same things. Okay? So we do need to recognize that the further away you get, you will be exponentially less attracted to that object. Okay? Same as with gravitational force. All right, let's look at a couple. Actually, I'm going to show you a couple of videos here that I didn't get to show you the other day to do with some of this interaction. Okay, so we want to calculate here. No, none of those. Or those. Where are the ones I want? That's the one I want. Okay, let's do this one together here, just to look at a simple gravitational field strength question. Right? We want to calculate the gravitational field strength on the surface of Mars. Okay, what we're given in this question is the radius of Mars. Okay, so we know Mars radius is 3.43 times 10 to the 6 meters. Right? And we know the mass of Mars is 6.37 times 10 to the 23 kilograms. If I want to calculate gravitational field strength, it's just big G times the mass of the body generating the field, that would be Mars, okay, divided by the radius of that body, or how far away the other body is from its center. Okay? So that's going to be 6.67 times 10 to the minus 11 times 6.37 times 10 to the 23, okay, divided by 3.43 times 10 to the 6 squared. All right, if we do that, okay, we should get 3.61, but we'll punch it in anyway. Okay, so 3.61 newtons per kilogram, or 3.61 meters per second squared. Either one, okay? It's the rate of attraction, not the force of attraction, that's being calculated when you calculate little g. All right, guys, there's going to be a gravitational field strength question on your unit exam. The thing that gets most people with it is not calculating gravitational field strength. Okay, you have to know it's a gravitational field strength question. There's really nothing else to do with it. You just use that formula. You don't ever set that formula equal to anything else. Okay, it's like a bank curve. If it's a bank curve, you know what formula to use. You only ever use one formula. Gravitational field strength is the same way. Okay, we only use this formula for gravitational field strength, nothing else. All right, I want you guys to try a couple here, okay, and then we'll go through them together. So I'm just going to pull them up on the screen here and you can work on. Okay, so I want you guys to work on number 4. Number 6, that's an easy one. Oh, I skipped a couple here, sorry. sorry, number 2, 2, 3, 4, 6. Okay, are the ones I want you working on. And then we might look at 8. It's not a field strength question, but we'll look at it, okay, in a bit.